In the last video, I said a few words about traditional mastering, and I spoke about how in order to gauge relative to all standards, you need separate master gauges, each of which has a bore dimension that matches the standard. And you would need at least three to match the major standards. If you have standards specific to an internal requirement, then you would still need an additional master gauge, because the basic conceit in traditional gauging for the N family is that you're always gauging relative to a zero state with a numerical zero on the dial face of the indicator. And that zero state represents a number which is not necessarily visible to the end user unless he's very familiar with standard, which, by the way, can cause some confusion. But that zero represents one of several dimensions, like 207 mils or 208 or 210 in the case of the male. We wanted to, and that changes for the female. What we wanted was a true universal gauge that was invariant with gender and invariant with standard. So it didn't matter what standard you were gauging relative to. It did not matter relative with regard to which gender you were gauging. It was truly universal, both in terms of gender and in terms of standard. So what we did was to machine our bushing in such a way that we made a relief cut in the bushing. And that little relief cut is represented by that step in the bushing. And when we gauge, we're gauging that step sits inside an annular ring, and it's the shoulder that's being seated on a flat surface. So we're mastering relative to a flat surface. And the punchline here is that the flat surface represented by the step in the bushing will be sitting on both the male reference plane, which is in a state of precession relative to the shoulder of the male pin, and it will be sitting on the female reference plane, which is in a state of recession relative to the front plane of the female pin. So what makes our gauging system unique is that when we master, we're mastering relative to a flat plane. And that flat plane is either the flat plane represented by the reference plane of the female, or the flat plane of the male, which is the reference plane of the male. So male, flat plane, you've already mastered relative to a flat plane. Female, flat plane, you've already mastered relative to a flat plane. And that means now that we have a truly universal solution to end gauging, because it doesn't matter what standard you're gauging relative to. It could be 39012, it could be Mil Standard 348, it could be IEEE 287 GPC and LPC, it could be a standard unique to a manufacturer of end gauges who is setting a standard, say, that's tighter than IEEE 287 LPC. But if you're using the traditional approach, that would mean that every time you set a new standard, you are boring a hole to a depth that represents that standard, because, again, the conceit in traditional gauging is that you're mastering relative to a specific dimension, and the zero state on the dial face represents having been zeroed to that dimension. But in the case of our system, you're mastering relative to a flat state, and therefore when you gauge, that same step in the bushing that you're measuring, that you're mastering relative to, that same step will be sitting on the reference plane in the female and sitting on the reference plane in the male. So you have a true universal solution with regard to standard, because now it doesn't really matter what your standard is. You will be mastering relative to all standards because your reference plane is a flat plane. And in the next video, I'll talk about the degree of freedom that allows you, and that ripples forward in terms of the way the gauging is done, and how we take advantage of that degree of freedom to change the nature of the dial face and end gauging to make it a lot simpler than the traditional dial face, which is always relative to an artificial zero state, which itself is relative to the depth of a bored hole.